Let's start with our impact parameter in case of Rutherford scattering. So we know that in case of Rutherford scattering, there is a target nuclei, that is gold foil nuclei, and here we will generalize it. We'll take any target nuclei, any nuclei, and here you have an alpha particle. Now this alpha particle is a positively charged helium atoms, which means if you remove the two outermost electrons of the helium atom, the nucleus of an helium atom is known as alpha particle, which contains two protons. So overall charge of an alpha particle is nothing but 2e. Let's say in this target nuclei, there are z number of protons. So z is the atomic number. You multiplied it with e, the electronic charge, you will get the total charge of the target nuclei. Now since this target nuclei is positively charged and this alpha particle is also positively charged, they will repel each other. And the distance from the center is called as impact parameter, here b. If this is the line joining the center, then the distance at which you allow the alpha particle to go towards the target nuclei, that separation is called as impact parameter. The alpha particle is going here, and as it moves, now we know it was supposed to move along this particular direction, but since it gets scattered at any angle theta, this theta is called as scattering angle. So let me write here, theta here is our scattering angle. The alpha particle is scattered due to the repulsion between the target nuclei and the positive charge of alpha particle. Let's see, this is delta p. So first of all, to figure out this delta p, we should know that what is our linear momentum initial. So this will be the direction of linear momentum initial, p1, because the particle is moving in this direction. And after scattering, it moves in this direction. So this is your p2. And we have to find delta p. Delta p is dependent on this p1 and p2. That's a change in momentum. Let's calculate it. So let me draw this diagram once again. So let's draw here p1. This is our p1, the linear momentum p1 initial, or let me call it as pi. And that is our pf, the final momentum. We can also write it as p1 and p2. Doesn't make any difference. Now we have to find the resultant. The resultant is delta p in that particular direction. So we can also, since it's a vector, we can also draw it again. And we can draw it like this. This is your pi. And we have extended this pi on the other side. And this is your pf. Then the resultant, we know it will be along this direction. That is your delta p. That's a change in momentum when it goes from the initial to final. So delta p is, we will say that if we follow our triangular law of vector addition, that the head of the first vector is connected to the tail of the second vector. So we can say that pf is nothing but delta p plus pi. And if I take this pi on the other side, delta p is nothing but pf, final momentum, minus initial momentum, pi. Now since the two vectors are subtracted, the resultant formula will be modified, and the resultant formula will be written as root under pi square plus pf square minus 2 times pi pf cos of angle theta between the two vectors. Be very careful. This theta is the angle between the two vectors pi and pf. In case if it was addition, here in place of negative sign, there will be a positive sign for resultant of the two vectors. So this we can write it here. We know that since this is a conservative field, so the linear momentum as well as the angular momentum for this whole system will remain conserved. We know that initial momentum pi, that is nothing but mass times velocity. So if it is conserved, then it should be equal to pf, the magnitude, not the vector. Be very careful. This is the magnitude. which is mass times velocity, will remain conserved. The direction might change, but this will remain conserved. Let's substitute it here and find our delta P. So this will be root under mv square plus mv whole square minus 2 times mv into mv cos of angle theta. This will give us root under m square v square plus m square v square minus 2 times m square v square cos of angle theta. Let's take m square v square common inside this root. So this will give us m square v square, and here we left with 1 plus 1 minus m square. Oh, we have already taken m square v square common out, so it will be 2 times cos of angle theta. You can re-multiply this and check if you get the previous equation. So if you multiply m square v square with 1, you will get the previous m square v square. If you multiply this with the second one, you will get the second term, and if you multiply finally with 2 cos theta, you get the third term. This m square v square can be taken out of the root and it will become mv, and root under you left with 2 minus 2 cos theta. So when you take 2 outside, this will be root under 2 into 1 minus cos theta. Now we know from our elementary mathematics that 1 minus cos theta is nothing but sin square 2 sin square theta by 2 by half angle formula. Let me repeat, 1 minus cos theta is 2 sin square theta by 2. So this 2 now, these two pair up and they can be taken out of the root. So it will be 2 mv, and root and sin square, that will become sin theta by 2. So this is our change in momentum delta P. Very, very important expression. This is delta P for this system when an alpha particle is approaching to the target nuclei. Let's move ahead and figure out an expression for impact parameter. Now we know that the force at any instant when the alpha particle is at a distance of r will be in this direction f at any instant. Then this force will make an angle phi with this change in momentum at any instant, where phi is any angle, azimuthal angle between f and delta p. So we can write by our Newton's second law that delta p is nothing but integration of f dt, where f is the impulsive force, delta p is the change in momentum, and t is that small interval of time. In this case, to make them equal, this f must be equal to f cos phi dt, where f is the Coulombic force of repulsion between alpha particle and the target nuclei. Let's write an expression for that. So we know from our elementary physics classes that f equals to 1 by 4 pi epsilon naught. What's the first charge? The charge of an alpha particle times the charge of the target nuclei upon the separation square. Let's write 1 by 4 pi epsilon naught as k, and this will become 2 times z e square upon r square. This is the force, Coulomb's force between the alpha particle and the target nuclei at a given instant of time. Since it is a conservative force, our angular momentum will also be conserved. So, let me write here equation 1. We will make use of this later. We will write now angular momentum expression so that we can convert this dt into d phi. How? We will see that. So, here, first of all, what's our formula for angular momentum? Angular momentum is L, which is equals to mvr, where m into v is the linear momentum and r is the perpendicular distance. So in this case, we can see that our linear momentum here for alpha particle is in this direction, and perpendicular distance, which is nothing but impact parameter in this case. So we can write this as mvb, and we know that velocity, the linear velocity, can be converted into angular velocity as omega r. V is omega r. So omega r into this already r existing here. So omega r square will be equals to mvb. Now let's take everything on the other side. So m cancels with m, and omega will be equals to vb over r square. Omega is nothing but angular velocity that can be defined as d phi by dt. That is equals to vb by r square. This is equation number 2. Let's go back to our equation 1. So our equation 1 says delta p is equals to f cos phi dt. So we can write this equation 1 as delta p is equals to integration of, what is f? F we already found it here on the left hand side. That was k times 2z e square upon r square. Let's substitute it here. So k times 2z e square over r square, and cos phi as it is, and dt, let's multiply up and down with d phi here, so that we can convert it into the angle d phi. And d phi by dt is vb by r square from second equation. So if we reciprocate the term on the left hand side as well as right hand side, this expression will be delta p will be equals to integration of 2k z e square upon r square cos phi, and what's our dt by d phi? Dt by d phi is r square by vb d phi. Before we integrate, let's take all the terms which are constant out of the integral. So this will be 2k z e square, r square cancels with r square, whole divided by vb integration of cos phi d phi. And left hand side it is delta p. This is our equation number 3. This equation 3 will give us the final result. But before that, let's find our limit of integrals. What will be the maximum variation in this angle d phi? So the variation of this angle d phi we can find from our diagram. We know that this is angle theta. So if this is angle theta, this whole angle will be 180 minus theta. Let me repeat here. This whole angle will be 180 minus theta. So this angle 180 minus theta will be splitted into two parts depending on this delta p, which is change in momentum. So one part will be pi minus theta by 2, pi minus theta by 2. Another part will be pi minus theta whole divided by 2. One will be negative and one will be positive. Let me repeat once again. If this is angle theta, this complete angle is 180 minus theta. So it goes from minus of pi minus theta by 2 to pi minus theta by 2. Let's substitute these values in our integral and find the integration. So let's go back to our equation number 3 and let's substitute the value of delta p which we found earlier here. So delta p here is nothing but 2 mv sine theta by 2, and on the right hand side this will be 2 kz e square upon vb integration from minus pi minus theta by 2 to pi minus theta by 2, integration of cos phi d phi. Now, what is the integration of cos? Integration of cos is plus sine. So it will be plus sine phi minus pi minus theta by 2 to pi minus theta by 2. And let's take everything on the other side. So taking this first whole parameter on the left hand side, 2 will cancel out with this 2. And mv square b sine theta by 2 whole divided by kz e square. Now putting the limits on the right hand side, it will be upper limit minus lower limit. So putting here upper limit, it will be sine pi minus theta, let's separate it, pi by 2 minus theta by 2, minus the lower limit which is sine pi by 2 minus theta by 2. And there is a negative sign, so that will make it plus. So sine 90 minus theta by 2, cos theta by 2 here. And sine 90 minus theta by 2, that will be again cos theta by 2. On the left hand side, it will be m v square b sine theta by 2 whole divided by k z e square. Now cos theta by 2 and cos theta by 2, that will be 2 cos theta by 2. Let's take everything on the other side to define our impact parameter b, and that will be equals to, taking everything on the other side, 2 cos theta by 2 already there on the right hand side, k z e square whole divided by m v square sine theta by 2. What is cos theta by 2 upon sine theta by 2? That is cot theta by 2. So our impact parameter gives us 2 times kz e square upon mv square and cot theta by 2. This is one of the expression. Another way of writing the same thing in terms of kinetic energy will be, we know that kinetic energy is half mv square. So we can take this 2 from the numerator below this mv square and we can write it as k z e square. Be very careful, this k is not kinetic energy. This k is 1 by 4 pi epsilon naught. This half mv square will form the kinetic energy ke, and this will be cot theta by 2. So this will be expression in terms of kinetic energy, and that is in terms of mass velocity. So this is our relation for impact parameter.